Hello, hi everyone. This is Professor Chen again. Today, I'm going to give you a 5-minute head up about Chapter 3, and the topic is torsions, and which is the second loading type for the material we're going to study. And the material models we're going to describe using is called the shaft. And for the shaft, we under the loadings at the two ends. For example, here at this end is T, and to get this in equilibrium, and the other end is the T is applied in the opposite directions. Or if you want to use your right hand rule, you're simply using your four fingers to circulate the direction here. Your thumb indicate the sense of the loading, and here we're using double arrow. So this is another equivalent symbol description. For this case, we're using our four finger circulate this direction, and the thumb is here. So that is the one here. So from here you can see using the double arrow symbols is a little bit clear, and this is in equilibrium positions. Okay, so this is the loading conditions, and to study the response of this shaft to loading, and again we want to see how the material deformed. And here you can see I pick up a small things here, and the loading on the top here I put it squares, and at here if you can see this clearly I put the squares cells here. So let me use this one to model the shaft, and here use my palm to apply the loading in this way. So you look this carefully, each slab basically originally is in horizontal positions. Once I twist it, basically it's each slab move away from the horizontal direction, deformed by little angles here. So basically, if you look at these little black cells, look at this carefully. And here I'm going to draw the deformation before and after deformation of this black cell. And the black cell initially is, for example, let me consider this one. So this is before the torsion is applied. And after torsion applied, that one actually will be moving to here. Okay, and here let me try to get this point, do the rigid body shifting to here. So basically the two figures can be even simplified into this. So from here you can clearly see the deformations of the shaft basically can be described by this angle. The change in angle of one side, and that is a response of the shaft to certain type of the loading, and which is torsion. And this angle actually, if you compare to our definition of the shearing strength, this is the shearing strength. We call it gamma. Okay, basically this angle equal to the shearing strength based upon our definition. So very clearly, due to the torsions, we measure the change in angle of each slab from his original horizontal directions. Then we measure the angle, and that angle right away exactly is going to equal to the shearing strength. Most of the time, to measure the shearing strength is a little bit inconvenient. So in terms of study of the shaft in torsions, and people come up with a good, convenient alternative is this one. Again, this is a loading. Let me turn around like this. So you can see this is the original cross section. Once I turn around, you look at this. You look at this mark. This is on before deform, and under deform and after deform, you can see this mark do a little bit twisting here. So here, let me draw the cross sections. So this is a side view of this, and this is the original mark here. So once we apply the torsion here, this mark will move to here. So basically become like this. and we define this angle is phi. The phi is called the angle of twisting. And we can relate phi equal to the shear strength by this. Let me say the radius is equal to c. C phi equal to L gamma. The L is the length of the shaft here. Okay, so here we are able to relate the strength equal to the angle of the twist. So this chapter, the first portion you're going to study is to learn how to formulate the angle of the twist in coupling with the definition of the shear strength. And from there, you would know how to quantify the response of the shaft to torsion. And that will be the first portions of this chapter 3. So once you learned how to calculate the angle of the twist equal to TL over GJ, and here let me describe, and this is the shaft, and under a torsion, and allow me to use the double arrow to indicate the direction, the sense of the torsion. And let me introduce, T is the torque we applied, and L is the length of the shaft. G is the rigidity modulus of these models. And what is J? J is called the polar moment of inertia. And that depends on the dimensions of the cross-section. For example, if this is a circular cross-section, and say this has a radius c, so basically this can be described by pi over 2 times c to the 4th power. Okay, and for other section type, you can refer to, when you learn, you can refer to the details. This is a fundamental questions here. And the other important things is here, you're going to learn if this is a cross section and this is under torsion here. The distribution of the shear stress is this. If we say we select arbitrary radial segment, the distribution of the shear stress is this one. The maximum at the outer surface, 0 at the center, their distribution is linear. So that means as long as you can determine any radial displacement, you can always predict the magnitude of the shear stress. The remaining chapter 3 will based upon those fundamental concepts here to further practical problems. And again, we're going to study indeterminate problems. And in particular, for this chapter, indeterminate problems, we will consider is the gears. Using gears to couple two shafts. And let me schematic draw the things here. So for example, one shaft is linked to one gear, and the other gear is come to here and then linking to another shaft. Okay, basically the gear set is used to couple two shafts, just like your shift in the cars, and to transmit the torque from this end to this end, and also to modulate the rotation of the speed of the rotation of the shaft. And this gears problems basically is turned out to be most challenging in these chapters, and based upon the feedback from students in the past. So you have to pay attention and when you learn this topic here. And also we have the last topic is called the stress concentrations. And this topic is very straightforward, it'll be easy, and we directly apply the curves and to approximate the magnitude of the maximum stress. And that pretty much covered the chapter 3. Thank you.